Hey hackers, Nerdwell here. Have you ever noticed that sometimes the best bugs are hiding in plain sight? Well, today we're going to take a look at finding and exploiting hidden functionality in Windows software by hacking DLLs. Before we start hacking Windows applications, it's helpful to have some background about the patterns and practices implemented by the developers of those applications. And many of these patterns and practices have been developed over the past 30 years and implemented by Microsoft themselves. In many cases, these have driven the technological advancements available to developers and the business processes that developers implement in their software development lifecycle. A big aspect of development in a Microsoft environment is code reusability and extensibility. And the basic premise here is developers want to write once, use many. So if they create some module with a capability, they want to be able to reuse that module within the same app, within other apps, and integrate with customers, vendors, partners, all sorts of other examples. But the basic premise is don't reinvent the wheel, write something one time and reuse it multiple times. Another important aspect of development in a Microsoft environment is the sheer scale and scope of some of these applications. They're so large that they require many teams working together, sometimes across continents and time zones, and definitely working under different timetables to build individual aspects of the application independently, but then put those components together to produce a final product that is cohesive and works well together. Along the same lines, by building a modular application, we can take a modular approach to maintenance of the application going forward. So if we need to implement a feature request or some security improvements to a specific element of an application, we don't want to have to rewrite or rebuild the entire application. It would be better if we can just work on the individual components and modules themselves and then reintegrate those into the larger whole, which is exactly what we find in most Windows applications today. Lastly, another very important aspect of working in a Microsoft environment is the ability to integrate with third parties. And a very common example here is many apps today, especially business, line of business type applications, will have some requirement to work with PDFs, even if it's just rendering a PDF or maybe modifying them and all sorts of other interactions. But developers don't want to have to reinvent this capability every time they develop a new app that needs to work with PDFs. So third parties have produced libraries that developers can integrate into their applications and then redistribute to the end customer that handles all that capability for them. The benefits here are, first, reduced cost to the end customer because the developer doesn't have to worry about creating all that capability. It also reduces the time to bring a product to market because the developer can grab ready-built modules and integrate them into their application. Lastly, it provides a standardized interface for a lot of these capabilities that developers can become familiar with and then reuse across a variety of different applications. Now, while all these different aspects bring many benefits to the table, they also bring some opportunities for accidents to happen, mistakes to be made, gaps to be present, and in each of those instances, we tend to find security vulnerabilities. So as bug bounty hunters, we want to understand how these patterns and practices impact the final product and how we can take advantage of that to find potential vulnerabilities to exploit. So, back in the day, when Windows became the most popular operating system on the planet, it was common to see applications written in Visual C++. And when we did that, they were compiled into machine code. They were the typical binary executables that we've all come to expect and that we reverse with IDA Pro and to really do much with and reverse engineer and make binary patches to them. You really had to bring them down to assembly and work with it at that level and then rebuild it from there. Obviously, that's quite a cumbersome process for the hacker, but as it turns out, that was also a rather cumbersome process for the developers and users as well. So even in the days of compiled C++ applications, we did have the concept of modularity, code reuse, and dynamic loading of application capabilities. And in a Microsoft environment, this was implemented through DLLs, dynamically loaded libraries. And the way it would work is if you were a developer and you wanted to use, let's say, a third-party PDF library, you would purchase that library from the third party. They would send you some DLLs. You would include them in your distribution, and then in your app, you would specifically call those DLLs and then import functions from those DLLs that you want to use in your application. It was a rather manual and explicit process, meaning you needed to specifically import that module and then specifically import individual methods and properties within that library that you wanted to use within your application. And while that worked well, as time progressed, Microsoft moved to a interpreted language environment, a just-in-time compiled environment, just like we see with Java and JavaScript and Python and all these other languages. We got Visual Basic, and basically when you built a Visual Basic app, it did not compile to machine code, it compiled to an interpreted intermediary language. And that led to the development of the .NET framework. And most of your applications today in a Microsoft environment are primarily .NET. And so we have multiple languages. The scale of variety in terms of different languages in the .NET framework seems to grow every year. But some of the key languages are Visual Basic and C#. What's important to remember here is when you build a .NET application, it does not compile to machine code. It compiles to an intermediary language. And actually, regardless of whether you wrote it in VB or C#, under the produced intermediary code at the end of the day is actually the same. So this provides a lot of flexibility. It also provides a lot of interoperability. So I can write a C# app that is able to leverage modular capabilities published by a Visual Basic .NET app. It's also been integrated into PowerShell very heavily, to the point that, as I've depicted here, you can actually invoke .NET code in PowerShell, and if you care to take the time, you could build an entire GUI-based app from PowerShell command line itself, with all the functionality and capabilities available to you in C#. So that's just a very brief history of DLLs and the progression of programming languages in a Windows environment. And this is going to play a very big role in how we target Windows applications in modern systems. We talked about some of the business cases for using modular approaches to software development. Let's take a look at some specific technical implications of this approach in modern applications. And when we're doing bug bounty hunting, I generally break the apps down into desktop apps and server-side apps. That doesn't necessarily need to be a web app. In most cases it is, but we also see a lot of times like network services, TCP, UDP, protocol services. But in general, those will have very similar attack surfaces as your standard web app, especially in a Microsoft environment. As we'll see here in a few minutes, they've gone very far to standardize the interface that the developers work with, regardless of whether they are writing a NetTCP app or a traditional IIS hosted app or a SharePoint app. So looking at desktop apps, one of the big benefits of DLLs, and in the .NET environment, DLLs of course still exist, but they are referred to as assemblies. So one of the big uses for desktop apps is the modularity for homegrown applications, the whole PDF viewer and modification library story that we talked about a minute ago. Another application for this modularity in desktop apps is, let's say I am a developer and I work for a company who has come up with some whiz-bang new software. And we have developed a core module that provides this capability, and we've developed one application that leverages that core functionality. But on our roadmap, in our business plan, we intend to develop a whole suite of apps that use this core functionality in all sorts of interesting ways. But of course, we don't want to have to rewrite and reintegrate that core functionality every time we build a new app in our suite. So by using this modular approach, we can develop it one time and then tie it into all of our subsequent apps in our suite going forward. That also plays into maintenance. So as we grow our suite and move down the roadmap, and now we have 5 different applications that leverage this capability, if we need to make a change to that core capability, we only need to make it in one place and then make small changes to the individual apps to make them integrate that new capability, but we don't have to redo it 5 different times. On the server side, we see DLLs and the assemblies are relied heavily upon in ASP.NET applications. These are your traditional IIS hosted web apps. And another good example of that is SharePoint. SharePoint makes super heavy use of assemblies, both Microsoft produced and in many cases third-party produced. So in addition to all the capabilities that SharePoint provides out of the box, you can get add-ons from Microsoft. There's Office Web Services, and then you can even build your own web parts that integrate directly into SharePoint, and all of these different components are compiled into DLLs referenced as assemblies in the web server configuration. And as we're going to see here in a bit, that plays a very big role in exposing the capabilities of some of these DLLs and assemblies to remote attackers. Lastly, we will see third-party middleware vendors often will use the same approach for server-side applications that we see in the desktop applications. And that makes sense. Basically, build something one time, license it, and then you can distribute it to any number of end customers to integrate with their platform. Likewise, the reverse is true. If you are a middleware vendor, a line of business application developer providing server-side software, you likely will want to provide your customers with the ability to customize that. And so a common way of doing that is to give your customers the ability to reference their own custom-built assemblies to either add on to the capability of your middleware or customize the default base behavior of your application. Now that we have some background about the Windows development environment, the patterns and practices that we can expect our developers to be implementing, and some of the high-level technical aspects of the modular assemblies that are in place in a Windows environment, let's take a look at some of the common bug patterns that we will encounter. And I think you may recognize many of these, and it's important to realize that what we see with the Microsoft approach to modularity is really just their way of addressing common business needs that many other vendors have also addressed in their own ways. And because these relate to business needs, we will see some of the same bug patterns across different technological implementations of the same capabilities. So, one that we'll see is deprecated code not being removed from release builds. And the way this usually will go down is, let's say let's take the example of the developer who has built some whiz-bang core application capability and a suite of 5 apps that make specialized use of that new functionality. Well, let's say that 4 of those apps are done using some element. We've come up with a new way of doing something, and we've integrated that into 4 of the 5 apps. But the 5th app, we haven't gotten around to it yet, and so we need to maintain backward compatibility. And so maintaining the premise of code reusability, we don't want to have to maintain separate modules for one app versus the other 4 apps. And so we may go ahead and just keep the old functionality in the module for the time being and still deploy that module with the other 4 apps. We're just not referencing that deprecated code. Or so we think. It's still there. And so as an attacker, our job is to figure out, are there ways that we can still reach those deprecated code paths in the other 4 apps that the developer has not anticipated? Another bug pattern that we'll see here is the reverse of that. New application functionality that has been prematurely included in a release build. So expanding on the prior example, let's say now we want to target app number 5, the one that's on its lonesome. It has not yet taken advantage of this new capability, but because we are sticking with one module, one core module for our application, and distributing it with all 5 apps, because 4 of those apps do use the new capability, obviously it needs to be in the module. And so that gets deployed with app number 5, and even though app number 5 is not actively taking advantage of that capability, the code is there. And so again, as debug bounty hunter, our job is to find ways to reach those code paths and exploit them in ways that the developers were not anticipating. Another example is inadequate sanitization of user input, basically. As I said, many of these will relate to like standard web API vulnerabilities. And you can't get away from the fact that user input cannot be trusted. And it's become pretty commonplace for developers to expect malicious code from web requests. And so we tend to see sanitization in most of those web apps. However, developers may be less likely to expect malicious input from endpoints or injection points that are not quite as easily accessible. So your standard user on the desk is not going to open up DLLs and expose all the different capabilities and start throwing, oddly formatted object structures at it just to see how it behaves. But as hackers, that's exactly what we want to do. It's a very similar process to how we might target a web app, but we're doing it through basically a different interface is all. Another bug pattern that we'll see with the use of DLLs and assemblies in Windows environments is naive routing of web app requests. And we'll take a look at some specific examples here shortly, but at a high level, web request routing in a Microsoft environment is a bit more complicated than in your traditional Linux, Apache environment or Tomcat or even microservices. In those environments, generally there is a clear and relatively statically defined set of routes that your requests are going to take. And you can know with a relative certainty that if a user provides some crazy endpoint, that it's not going to reach any executable code. One exception, or the closest exception to this in that environment may be like, let's say you have all your PHP files in a CGI bin folder. So if you put a new PHP file in that folder, it just inherently will be executable and could bring down your server. However, because you can just simply list the directory contents of that folder, web server admins are more easily able to identify malicious changes and inspect those files themselves because they're just clear text. It's scripting based capabilities. In contrast, with a Windows IIS hosted web app, it may just reference a DLL, and then to actually understand what happens when that DLL receives that request, you actually have to kind of crack it open and dig in there and do things that many web server admins probably are not familiar with. And so it's that element of that lack of visibility that introduces some potential vulnerabilities that we'll take a look at. And you would be shocked the number of vulnerabilities I have found in Windows apps that include hard-coded keys, passwords, and tokens. And I'll throw out a couple generic examples here. And many of these are implemented in this modular approach. And so here's how it can go down. Let's say I'm a developer, and let's say I'm that developer with my whiz-bang core functionality and my 5-app suite of products. And let's say in this core functionality I have some complicated cryptographic operations that each of these 5 apps needs to take advantage of. And of course, I don't want to have to do that 5 times. I want to write that difficult code one time, put it in a module, redistribute it, and so on. However, let's say that even though I only did it one time and I spent my time on it, I still messed it up because crypto's hard. And I hard-coded some key in my code. Well, now, the very fact that I'm using this centralized module to distribute this capability to all 5 of my apps is working against me, because now all 5 of these apps are vulnerable to exploitation of this same hard-coded key. And that opens the door to all sorts of possibilities. Maybe I'm a user of app 1, and because it shares a key with app 3 by way of this centralized module, I'm able to access the data from some other user from some other company using some other app who has no idea who I am. That's one example. Another that I've seen is it's relatively common for desktop apps nowadays to host small little web services for things like mobile app integration or peer-to-peer communication. And so a lot of times the nature of this capability requires it to be pretty low complexity. The users who are interacting with it don't want to type in long passwords, or potentially don't want to type in any passwords. And so that's a perfect example of where we might see some hard-coded passwords. Lastly, in the .NET framework environment present in modern Windows environments, what we have is basically an object-oriented runtime environment. And the idea is you load your DLLs, which are assemblies, into the system, and you can decide whether you want to load them at a system-wide level or just keep them semi-private. But as you may have noticed, many of the benefits of using this modular approach require you to register your assembly with the system so that it is available to any process that wants to take advantage of the capability. And when it does that, it's basically exposed through object-oriented classful basis. So if I'm an app who wants to take advantage of the capability exposed by your module, I don't need to know the name of your DLL. All I need to know is the class, the object that I want. And I just include that in my app. And then Windows and the .NET framework takes care of all the background legwork of figuring out where that DLL resides and loading it into memory and creating execution entry points and so on and so forth. However, this also introduces some interesting attack vectors because similar to insecure Java object deserialization, many Windows apps will instantiate objects at runtime based on user input. And in fact, Microsoft has gone to great lengths to simplify this process for developers. The idea from Microsoft's perspective is they want the developers to be able to implement some of this standardized functionality, like object deserialization, with the minimal amount of code and even the minimal number of clicks. And so when you have a framework in the background doing a lot of this stuff automatically, it's inevitable that developers and server admins are not going to understand how it works or even when it is at work. Of course, as bug bounty hunters, that presents a golden opportunity for us to take advantage of insecure object deserialization. Let's take a look at some tools that let us peek inside Windows assemblies and executables in a .NET environment to glean some information and, in most cases, reverse it to human readable code. So just to reiterate, in the modern .NET framework environment, code is not compiled to machine code at build time. It's compiled into an intermediate language that is then interpreted by the .NET framework at runtime and then converted to machine code. What that provides us as attackers is the ability to trivially reverse any app, any .NET app, to human readable source code whenever we want. And there's actually many tools to do this, and in fact Microsoft themselves have produced a tool that is widely available. It's called ILSpy, IL meaning intermediary language. And this actually is available in the Microsoft Store. So if you're running Windows 10, you can just open up the Microsoft Store, type in ILSpy. It's rated 4.9 and published by Microsoft. And basically, it's a very useful tool. It lets you introspect into a DLL or an executable in a .NET framework environment and not only see the human readable source code, but also the references that an app has. So it can get a little bit tricky to determine all the different assemblies that a given application uses, especially when some of those assemblies are not even contained within that application's program files folder. If it's registered with the system, it'll be in what they call the global assembly cache, the GAC, and that's a system-wide folder. So the only way that you can really understand all the different assemblies that an application references is to use a tool like this, which goes through and identifies all the class references within that project and list them here for you. And from there, you can drill down and start finding all sorts of interesting things. And so the way I usually use this tool is with an application that I don't know much about. Let's say it's a Windows executable, .exe. I will open it up in this app and it will give me basically a map of all the different assemblies that are referenced by that main application, and that drives the rest of my research. Now, while ILSpy is a great tool and it's free, it's from Microsoft, it's well supported, it does have its drawbacks. It's not the most user-friendly in terms of searching for things through multiple files, and it has a somewhat outdated user interface. So another tool that I will use is from a third-party company called JetBrains, and the product is called DotPeek. And this product is actually designed for developers, and it's part of a suite. You can get all sorts of different products from JetBrains, and most of them you have to pay for, but DotPeek is one that they offer for free, and it provides many of the same capabilities as ILSpy, but it provides some additional functionality, and it also provides a more modern user interface than ILSpy. So usually I will use DotPeek for the actual code review that I want to perform. So when I start to get down to the nitty-gritty, I've identified exactly which assemblies I want to dig into. I'll open them up in DotPeek and then go through them line by line, and it is with this tool that I have found several instances of hard-coded keys in a variety of different types of applications. And, you know, there is the argument that you could just run strings on some of these apps and see those keys. And that's true. However, at least in my experience, I don't think I would have found some of the ones I found if I had just tried to find them with strings, because they're random strings of data. And when you run strings on a Windows app, you get a whole bunch of nonsense. Some of it's, 25 characters. It looks like a password, but it's actually not anything. And that can be very easily confused with something that looks almost exactly the same, but is actually referenced as a key inside the code. So being able to look at the actual source code and see what the code paths are can take you right to the place where you will be able to make sense, have the right contextual data to recognize what is being used as a hard-coded password or hard-coded key and what is not. So let's take a quick look at how I use DotPeek in my workflow. So we'll do a quick demo and I will walk you through how I... One thing that I like about DotPeek over ILSpy is that it actually lets you add an entire folder to its tree here. So let's say I'm just going to go to my documents and I've placed some executables and DLLs in this LevelUpX folder. So I'm going to tell it to open that folder, and it's going to identify all the executables in that folder. And one thing it's very helpful is actually it will determine if it is even supported by DotPeek, meaning is it a .NET app. So let's take a look here. I'm going to go ahead and open up command prompt and so as you can see, this is what I have, and I'm just going to run this. Oh. Okay, we're going to run this executable. This is the little POC I wrote. It is a Visual C++ compiled binary, an executable, old school. And I did that on purpose. It's a command line app. But I did that on purpose so that we can see when we pull it up here in in .peek, it gives us basically some very basic information. It reads the PE header from the file, but that's about it. And what I find in the wild is a lot of applications actually still do leverage some old school compiled, basically they call it unmanaged code. It's not .NET code. And many times it will be like some old third-party library that provides some capability that that application needs, but hasn't been maintained by the original vendor. And so they basically are carrying this legacy code in their product. And this will help us to find that. And so just because .peek can't deal with it doesn't mean we can't target it. It just means we got to use some other tools. In this case, I would use IDA Pro, reverse that, and see what I can find. I would also go through the managed code, the .NET code, the stuff that is supported by .peek, and find where does it reference that unmanaged code and how is it referenced. That interaction between managed .NET code and unmanaged old school compiled code is a perfect gap to find very impactful vulnerabilities. Because in that old school code, you're going to find things like buffer overflows, string format vulnerabilities, integer overflows, all sorts of good stuff. I also put some SharePoint files in here. I had just copied these from a SharePoint server to demonstrate. So what we'll do is we'll start with this one. So Microsoft SharePoint provides a basic search capability, which is implemented by this library. And so if you look at the configuration, the web server configuration in a Microsoft SharePoint server, you will see that there's an endpoint, a virtual directory basically, that's mapped to an app that references this assembly. And it references it at the top level, Microsoft.SharePoint.client.search. And that's where it stops. It goes and it loads this assembly. And that's important because from that point forward, how it handles the request depends on how this DLL is written. And so, as I kind of touched on earlier, in many traditional web applications, the endpoints exposed by the app are relatively static. In a .NET application, it references an assembly and then looks at that assembly to decide, okay, does the specific endpoint that the request has indicated match a web exposed function, method, or property in this assembly? And so it's very dynamic. And so that opens up the door for, let's say, a developer copy-pastes some code and doesn't realize that they've just copied a very important attribute which makes that method web accessible. And all of a sudden, they've now exposed some backdoor capability that they did not intend to. And believe it or not, I have seen this in several instances. One very common example of this is when an application needs to implement some sort of automation, like a bulk import or bulk edit capability, and it needs to be called by other scripts and processes, and they don't want to like put a password in a script, for example. And so they will have the idea of, okay, well, we'll just make this quote unquote hidden endpoint that only we know about, and when you call it, it provides you access that other endpoints require you to have authentication to access, but if you call this specific one, you don't have to authenticate. Well, because we can go in here and look at the code, we can trivially identify those. Now, this is a SharePoint DLL. I have not found any vulnerabilities in this one. I'm just using it as for demonstrative purposes. So when you call this query endpoint, go and pull this up. When you call it, what it does is IIS actually goes in here, opens up the assembly, and it looks for this remote attribute. And so this can be on methods, it can also be on properties. And so over here on the left-hand side, these little icons indicate these are methods, these icons indicate their properties. So what the properties mean by being remote is they have getters and setters. And so basically this corresponds to get and post. And so if it has this little remote attribute before that object, or that class member is what it is, then it also has to be public. So these two elements right here together make this property accessible through the query interface using this code for gets, this code for posts. And we can go through the code and enumerate all the different ways that we can target an application. Now, this being a Microsoft app, these are all publicly documented. If you go to Microsoft's website, if you just Google Microsoft SharePoint.client.search.query, it will take you straight to a Microsoft website that says the Microsoft SharePoint Client Search Query namespace. And it basically provides a nice listing of all this stuff. However, for third-party apps and apps that you're going to encounter in Bug Bounty, they very likely do not have that kind of documentation. And so that's where this research can be helpful to help you find basically undocumented backdoor endpoints that provide sensitive capability. And you had the bonus of you actually get to see the source code. So not only can you identify potential endpoints that are undocumented, you can see what they do when you call them. You can't get much better than that. One last thing I'll show, or point out rather, is this remote attribute is actually like a Microsoft internal attribute. They tell developers don't use that, but in .NET environments, there is an equivalent, and it says web method. So basically, if you open up any assembly that is used in an ASP.NET application, you want to be looking for remote in brackets or web method in brackets. And if you see either of those, then odds are that member, that class member, is accessible through the API, the web accessible API. Another tool that I find very useful when I'm doing testing of a Windows application is netstat. And so, as I mentioned before, in many cases, desktop client-side applications are opening network services for various functionality. One common reason is mobile app integration. Another is local network peer-to-peer communication. And so what I'll do is I'll run netstat once before I do anything with the app. Then I will launch the app and then, maybe exercise the different capabilities of it. Then I'll run netstat again, compare those snapshots, and see if any ports were opened. When I run netstat in a Windows environment, I do the -B as in Bravo, A, N as in Nancy, O, bano flags. What that shows you is not only the ports that are open, but the actual executable that is tied to it. Of course, you need to run this as an administrator in an elevated command prompt, but in many cases, this will tell you specifically which application is listening on a given port. And from there, I will just run with it. I'll open it up in DotPeek and walk the different code paths and find some vulnerabilities. Well, thanks for joining me today. I hope that was helpful. Hopefully you got some new techniques that you can integrate into your hacker toolkit. If you have any questions, please feel free to reach out. You can follow me on Twitter, and happy hacking.